Welcome back. In this lecture, we'll be talking about solving polynomial and rational inequalities. We solved linear inequalities back in chapter 2, and for that we did it purely algebraically. But we're going to talk here in this section about solving inequalities where it's a rational function or a polynomial. Algebraically will be one way for us to do it, but another way will be via graphing. Before I get too far into this, I just want you to note that it says here supplementary, and it says that because this is not actually a section in the textbook itself. If you're having a look at the course notes, if we were to flip towards the very end of the course notes for this chapter, you'll notice that after the practice problems that are in the text from 5.1 through 5.6, then there are extra practice problems for that supplementary section here, solving these inequalities. And I've got the answers following on the last page. So just be aware that we do have practice problems for this section along with solutions to it. So for the first half of this lecture, we'll be talking about solving our inequalities graphically. So if you've got a graph of f of x, then it's easy enough to solve an inequality involving f of x, because if you want f of x to be greater than 0, remember that f of x, these are the y values for your function, the y values that are greater than 0. That would be what you're interested in. Where are you above the x-axis? If you're looking for where is f of x less than 0, in other words, where are the y values less than 0, where are you below the x-axis? And of course, for greater than or equals to or less than or equals to, you're interested in where you're above the x-axis or where you're below the x-axis, but also including where you are exactly at the x-axis, where is it equal to 0. So for these inequalities, really it's just a question of where are you above or below the x-axis. So for this example here, we've got a polynomial f of x, and I haven't given it labeled. I've just said that this is f of x, some sort of a polynomial, and you want to solve these inequalities. Solve for where is f of x less than 0, where is it greater than 0, less than or equals to, greater than or equals to. So for part A, if we're looking for where is it strictly less than 0, where are we below the x-axis? If you're looking at your graph, you're below the x-axis only for this little chunk here, which is between -2 and 0. So where are you below the x-axis? From -2 to 0, not including the -2, not including the 0. Not including the -2 because that's where you're exactly at the x-axis, and same thing with 0 because, again, that's where you are at the x-axis. Now, the difference between A and B is that in A, we were only interested in where are you below the x-axis. For B, we're interested in where are you below or at the x-axis. And so some of it will be similar to what we had before, because we'll still be including the where we're below, which is between -2 and 0, but we'll also be including where we're at the x-axis, which would be at -2, at 0, and also at 3. So if I were to express that, I would say, and I'm just going to clear this up a little bit. If I were to express that, I would say it would be all the points from -2, including -2, up to 0, including 0, and then, and this is the part that might look a little bit weird, to include a single value, to include that point 3 using interval notation, the single value of 3 would be all the numbers from 3 up to 3, including the 3. So in other words, the interval from 3 to 3, including the 3. So that's me expressing here all the values of x where we're either below the x-axis or at the x-axis. So everybody from -2 to 0, including those endpoints, as well as from 3 to 3, including the 3. Now for B and C, for C and D rather, For C, we're interested in where are we above the x-axis. So C is just where is f of x greater than 0. And there's three areas: everything to the left of -2, everything between 0 and 3, and everything greater than 3. We're not including the 3 here because 3 is where we are at the x-axis. And for part C, we're not interested in where are you at the x-axis. We're interested in where are you above the x-axis. So we're above the x-axis from the far left up to -2, not including the -2. We're also above the x-axis between 0 and 3, not including the 0 or including the 3. And we're also above the x-axis when we're greater than 3, again, not including the 3. All right, so last thing that we want to do is D, which is where are we greater than or equal to f of x, greater than or equal to 0? Where are we above the x-axis or equal to the x-axis? And we know, again, it's going to include all those parts that we originally had, the parts that were to the left of -2 and between 0 and 3 and greater than 3. Only now we will include the 3 and include the 0 and include the -2. So when I say where are we at or above the x-axis, the answer is, well, for D, everything from the far left, I'll make that look more like a round bracket, there we go, up to and including the -2, so square bracket around the -2, together with everything from 0, including the 0, onward. Because, of course, if you notice here, once we get to x being 0, at every point afterwards, we're either above the x-axis, at the x-axis, or above the x-axis. So in other words, that whole interval of everything that's 0 or larger, that's a place where we are at or above the x-axis. So I would say from 0 onwards. Okay, so for this, we just need to graph our function, and then once we've graphed our function, we're going to solve for where is it greater than 0, where is it above the x-axis. And so for this, it's already given to us in factored form, thank you me. So that saves us the work for finding x-intercepts. That'll be easy. But of course, remember that since this is a polynomial, we're also going to need to find two things from the unfactored version, the expanded version. We'll need to know what the leading term is, because that will tell us what the end behavior is like. And we'll also need to know the constant term, because that will tell us our y-intercept. So I'll just do that right now. I'll get my leading term out. And remember, we find our leading term by multiplying the leading terms together of all of our factors. And so in the first factor, the leading term is -3. In the second factor, it's x. In the third factor, it's x, and it's being squared. And in the fourth factor, it's x. So our leading term, -3, there's an x that's being squared. There's another x that is -3x to the 4. The other thing that we'll need to do is come up with our constant term, and for the constant term, we will take all of our constant terms and multiply them together. And -3 is the constant term in the first factor, -1 is the constant term in the next factor, -2 that's being squared for the next factor, and -5 for the last factor. So our constant term is -3 times -1 times 2 that's being squared, and times -5. And if we were to multiply this all out, this would give us -60. So that tells us a couple of things. First thing it tells us, the leading term tells us about our end behavior. Our end behavior would be the same as the end behavior for the graph negative 3x to the 4. X to the 4 would look sort of like a parabola opening upward, so going up on both sides. Negative 3x to the 4 then would be going down on both sides. So I know for this polynomial we'll be going down on the left and down on the right. The other fact that we have is, courtesy of our constant term, we know what the y-intercept is. For a polynomial, the y-intercept is found by finding the constant term. Since the constant term is negative 60, then my y-intercept is the point 0, negative 60. Okay, so the next thing that I'll need to do, now that I've got the end behavior and the y-intercept done, I'll need to do x-intercepts and talk about behavior at those. So that'll be my next bit of business that we'll do. We'll do our x-intercepts. And so once we've done that, we'll talk about the zeros, their multiplicity, and the behavior at the x-axis. So the first thing for us to do is to go back and find what our x-intercepts are. And for our x-intercepts, we're letting our polynomial be equal to 0, and it's easy enough for us to see that there are 3 different x-intercepts that we're going to have. One of them will be at 1, 0, the other one at negative 2, 0, the other one at 5, 0. So we have 1, negative 2, and 5. Those are our zeros for this polynomial. So our zeros are 1, negative 2, and 5. Our x-intercepts, 1, 0, negative 2, 0, and 5, 0. And now we just need to go back and talk about multiplicity and behavior. And so for those x-intercepts, 1, negative 2, and 5, notice that x minus 1 and x minus 5, those have odd multiplicity. So that means that you're going to cross at 1 and at 5. And for the other x-intercept, which was at negative 2, notice that this factor that it came from, x plus 2, has even multiplicity, has multiplicity of 2. So we had multiplicity of 1 and 1, which is an odd multiplicity for x being 1 and x being 5. We have even multiplicity, a multiplicity of 2 for x being negative 2. And if we have even multiplicity, that means that we will touch the x-axis. Okay, so let's put things together here. So we have 3 x-intercepts at 1, negative 2, and at 5. We had our y-intercept was at 0, negative 60, and that our end behavior was going down on both sides. So 0, negative 60, and our end behavior going down on both sides. Good, good. And so the last thing that we need to do is just fill everything in, and we knew that we have at 1 and at 5, this is where we're supposed to cross the x-axis. That at negative 2, that's where we're supposed to touch the x-axis. So let's put all of that together and say at negative 2, we're supposed to touch the x-axis, which means that we're going to have to go down and make our way to the negative 60. And we're going to have to make our way up to make it to the next x-intercept. At 1, we're supposed to cross the x-axis, which makes sense because then we'll have to come back down at some point and at 5 we cross again, and yes, that's exactly what happened. So we do have everything that we needed to accomplish here. We have the Y-intercept, we passed through it. At the X-intercepts, we touched and crossed as predicted. That our end behavior was going down on both sides, again, as predicted. So there we go. I can now label my graph. This is f of x being -3 times x minus 1, x plus 2 squared, x minus 5. And now that I've graphed f of x, I can go back and address the original question. The original question was, we wanted to use this graph to solve where is f of x greater than 0. In other words, where is our graph above the x-axis? So let's go back to our graph here and say, where are we above the x-axis? It looks like we're only above the x-axis between 1 and 5. So for the question of solving f of x greater than 0, the solutions is just the interval from -1 to 5, not including the -1, also not including the 5. We're looking for where is it greater than 0, so where are we above the x-axis? We're not including the equal to 0, so we're not including the points that actually are x-intercepts. We'll do one more little bit of graphing here. Graphing g of x and then doing the same thing, using that graph to now solve a problem. In this case, solving this inequality, where is g of x less than or equal to 0. First, just to factor g of x out, the numerator factors as x minus 1, x plus 1. And nothing cancels here whatsoever, so we know that for our domain, it's all the x values except x cannot be -2. We know for vertical asymptotes, it should have a vertical asymptote x equals -2. We also know that there's no horizontal asymptote, and that's because the degree of the top is larger than the degree of the bottom. We also know that there are no holes in this graph, because anything that was a factor of the original function remains a factor of the denominator of the function once it's in simplest terms. In other words, we didn't get rid of any of the denominator factors, so there are no holes in this graph. So vertical asymptote, one of them, no horizontal asymptotes, no holes. If we're looking for x-intercepts, x-intercepts happen when the numerator is 0, which that's already been factored out, and so we can find that x is equal to 1 or x is equal to -1, or in other words, the point 1, 0 and the point -1, 0. Notice for behavior that both of these factors show up exactly once, which is odd multiplicity. So for both of these, we're going to cross the x-axis. So both x plus 1 and x minus 1 had a multiplicity of 1, which means that for the behavior that we're going to do, we are going to cross the x-axis at both of those points. And then lastly, we also want to find our y-intercept, and our y-intercept happens when we let x be 0. So we're going to take our original polynomial g of x, which of course is the same as the simplified version of g of x, put in 0 for x, and we will see what we get for our y value. And when we put in 0 for x, just checking, yes, so 0 minus 1, 0 plus 1 over 0 plus 2. That simplifies to give me -1/2. So we've got the point 0, negative a half. All right, let's get to some graphing here. So we have 0, negative a half as my y-intercept, and I'll need to label that. I have the x-intercepts 1 and negative 1. All got those plotted. I have a horizontal asymptote of x being negative 2, so we'll graph that. And we've got enough information to figure out what's going on the right side of our graph. So on the right side of our graph, it's pretty clear that we're going to have to make our way from this y-intercept to both of those x-intercepts. And we also know that we're crossing the x-axis at both of those points. So we must be going up. That makes sense, heading towards that x-intercept. And at 1, we're also going to cross the x-axis, so going up, which makes sense because we don't have any vertical asymptotes, so we're just going to continue going up forever. So that's answered part of this graph. What does it look like? We know on the right side of that vertical asymptote, we are going up on one side and up on the other. The next thing that we'll need to address is what happens on the left side of the graph. What happens over here? And so again, this is something where we'll need to pick a test point so that we'll know what will happen. I know a couple of things already. I know that whatever my point is, I'm either going to have to go up to the positive side of that asymptote or head down to the negative side of that asymptote. I also know that I don't have any x-intercepts, so whatever I do will not involve me crossing that x-axis. So let's go back and let's find ourselves a test point. And so for me, the test point that I'm going to choose would be the point x being negative 3, since I'm looking for my little test point that I'm going to have. I'll choose x being negative 3, and so now I can find what my y value needs to be. And so in the numerator, we have negative 4 times negative 2, and in the denominator, negative 1, and that gives me negative 8. So I have then the point negative 3, negative 8. That'll be a point that's on my graph. So I'll plot that. Negative 3, negative 8. There we go. And so I know a couple of things that are going on here with this graph. I'm just going to make my vertical asymptote a little bit longer here. Again, I said you could either be going up from that point towards the vertical asymptote, or you could be going down. And you couldn't be going up because if you did, you would have to cross the x-axis, and you know that you don't. So that means that from this point, negative 3, 8, we must be going downward. And then leaving that point on the left side of it, you could either be going up, but that would mean you'd cross the x-axis, and you're not doing that. So that means that at some point you must turn around and start heading back downward. And so again, just like the other graphs that we've done before where there's a turning point, I don't know exactly where it is. So it's possible that, for example, this graph maybe immediately starts turning down, or maybe we get a lot closer to the x-axis before we turn down. There's no real easy way for me to tell this without calculus, so all I can do is give a general shape to my graph, which is it'll go up and then eventually start going down. I should still label that point, negative 3, negative 8. I'll also need to label that y-intercept 0, negative a half. And I should also label my function. And again, we're going to label it as g of x is x squared minus 1 over x plus 2. And then there we go. This is a nice, well-labeled graph of my function. Now, that wasn't the original question. The original question was not just to graph it, but once you've graphed it, solve the inequality g of x less than or equal to 0. So let's do that here. So I'm just going to make a little spot here where I can write this in. So if we're solving g of x being less than or equal to 0, we're interested in where are you below the x-axis or at the x-axis, and there's, for the solutions for this, two regions. Everything from the far left up to -2, you are below the x-axis. So for sure, everything from far left up to -2, not including the -2, because of course you can't. That's a vertical asymptote. There's nothing going on there. Also, we're below the x-axis between -1 and 1. And in fact, we're equal to the x-axis. We're at the x-axis at -1 and +1. Since we're looking for where are we below or at the x-axis, then we will then say that it's everybody from the far left up to -2, together with everybody between -1 and 1, including both of those endpoints. And there we go. That's my solution to that inequality problem, solving where that inequality g of x is less than or equal to 0. Just one little bit of commentary here before we end this part of the lecture. So you'll notice that for some graphing problems, for example, this little polynomial graphing problem, it wasn't too big of a deal because the polynomial was already factored, or if it was a polynomial that was easy to factor, graphing polynomials never really takes that much time and effort. Finding intercepts, discussing behavior, and behavior, put it together, and there we go. So that wasn't as much of an ordeal. However, even for something that's a relatively small rational function like this one, there's so many things, so many properties to look at when you're graphing a rational function that to get to the point of finding out what g of x looks like, that actually takes quite a bit of work. And so what we're going to see is that there's a second way that we can use to solve inequalities that will not require us to come up with our graph. That will just instead require us to do some numerical work. And that's what we're going to see in the second half of this lecture.